Good morning, welcome back. I've got my coffee here, I'm all ready to go. Hopefully you are too, and you have your guided notes ready. Today we're going to be talking about the gas laws, and the gas laws are really interesting from a mathematical standpoint because we get to use things like temperature conversions and fractions and algebra all at the same time. From a practical standpoint, the gas laws tell us what happens to a gas when the conditions change. For example, if the pressure changes, how does that affect the temperature and the volume of the gas? And it's really interesting to be able to do this type of math and figure out what's going to happen without actually having to perform the experiment. We're going to be using a couple of laws. Perhaps you've heard of them before. We'll have the general law of perfect gas, and then we'll talk about Charles's law and Boyle's law, things that happen when either the volume, the pressure, or the temperature are constant. But before we begin, let's talk about pressure. Slide this up a little bit. Okay, the first thing we need is the difference between gauge pressure and absolute pressure. Pressure is defined as an amount of force per unit area. So if you're working with things like pounds, we often measure pressure in pounds per square inch. On a gauge, you might see that abbreviated as PSI. If we talked about atmospheric pressure at sea level, that is about 14.7 pounds per square inch, PSI. But everything is subject to atmospheric pressure. So for a gauge measurement, we really don't want to count that. A gauge should be calibrated to read 0 PSI when it's not exposed to any other forces. Absolute pressure is pressure that's referenced against a vacuum. That means we have to count the atmospheric pressure as well as any other pressure that might be acting. So let's see. Absolute pressure is pressure that is referenced against a total vacuum, so it includes atmospheric pressure. In the measurement. If you want to figure out absolute pressure from gauge pressure, we just add in atmospheric pressure. So we add in the 14.7 psi. Keeping all of these pressures separate and so we don't get confused, we use some different units. If we talk about PSI, pounds per square inch, but it's coming from a gauge, we say PSIG. And if we talk about absolute, we say PSIA. So PSIG is that absolute pressure with atmospheric pressure taken out. And absolute pressure is the gauge pressure with atmospheric pressure factored in. And hopefully by now you're looking at these two formulas here and you're realizing that all you really need of these is one of them. We've got that idea of inverse operations, right? To undo adding 14.7, you just subtract 14.7. So usually we're given a gauge pressure and we have to add atmospheric pressure in to figure out the absolute pressure. Okay, so let's move on. The general law of perfect gas. Temperature, volume, and pressure of a gas are all related by a formula that's called the general law of perfect gas. So let's just write this down first, and then we'll talk about what it means. P1, that's P with a small subscript of 1, multiplied by V1, divided by T1, will always give us the same value. So if we had P2, we could multiply by V2 and then divide by T2. So the first thing you might be wondering is, what are all these 1s and 2s? Whenever you have a 1 as a subscript, this talks about your beginning measurement. So P1 is the pressure the first time we measure it. V1 is the volume the first time we measure it. T1 is the temperature the first time we measure it. This is something that we call the initial condition, the beginning. And then later we go back and we take another measurement. So when you have 2 as a subscript, this talks about a measurement that happens later on. But these are all taken at the same time. We started here, we took all these measurements, we waited for a while, and then we took another set of measurements. So the number 2 as a subscript indicates that we've taken another measurement later on. Before we can use the general law of perfect gas, we have to make sure that we are aware of the conditions. I mean, this always works, but only if we're careful with the math and with the units. So let's flip over to the next page. The first thing that has to happen is that everything needs to be measured in absolute terms. And what that means for you in terms of pressure is that we can only use absolute pressure, PSI-A. The same thing is true for temperature. We can only use temperatures that are measured in absolute terms. That means Fahrenheit and Celsius are out. We can only use Kelvin and Rankine. And the other thing we have to be careful of is that we have the units for measurement always the same as time progresses. So you can't talk about volume in cubic inches the first time you measure and cubic feet the second time you measure. We have to make sure we've got the same units happening all the time. All right, so let's just try an example and see where we go. This one has no context, but that's okay. This is just some practice so that we can make sure we have everything organized in its place and we know what needs to happen to get us where we want to go. So let's just start by putting things into a table. I like to make 2 tables, one that keeps track of what I have, and then one that forces me to think about converting things over into absolute if necessary. So let's just put some labels in, some values inside of our table. P1 is 8, and that's PSIG. Always a good idea to keep your units handy so that you don't forget what they were. The initial volume, V1, is 17. Those are inches cubed. The initial temperature, that's T1, is 30 degrees Celsius. The second temperature is 40 degrees Celsius. And again, those units will help you stay organized, and just in case you put the 40 someplace else, you'd see that that was in the wrong spot right away. The second volume is 24 cubic inches. And the final pressure, we don't know. So we'll call it X. So what's happening here? We've got some gas. The volume increased. That tends to ease up on the pressure. But the temperature also increased. That usually tends to increase the pressure. So I'm not really sure what to expect here for this second value of pressure. So let's calculate and see what happens. The first thing we have to do is take this PSIG and turn it into PSIA. So 8 PSIG plus 14.7 is going to give us 22.7. And of course that's PSIA, and we'll put it up here. The second pressure, we don't know. Volume doesn't have any absolute measurement. I mean, it is absolute measurement already. So 17 inches cubed is here, 24 inches cubed is there. The temperatures need to change. we have 30 degrees Celsius. We need to turn that into a Kelvin temperature. And of course, you remember that to turn Celsius into Kelvin, we have to add 273. So that should give us 303 Kelvin. Right now, if you're thinking that I should be saying something like 303 degrees Kelvin, actually, that's not quite true. There's not really anything called a degree Kelvin, but a lot of people say degrees Kelvin. So I can do this like we did in your reading. That's fine. If I leave it off, just understand that it's technically not wrong. All right. Anyway, let's do the other temperature. 40 degrees Celsius plus 273 is going to give us, well, 10 more kelvins, right? So that will be 313 Kelvin. There we are. All right. So I'm going to change colors here. There's a lot of blue happening. We have that general law of perfect gas. It says that P1 times V1 all divided by T1 is exactly the same as P2 times V2 all divided by T2. So our job is to first start off, be careful, and put everything where it belongs in the formula. Okay, so P1 is 22.7. Start your calculation here in the middle of the page because we're going to do some things on either side of it in just a second. So let's see, 22.7 multiplied by V1, which was 17, all divided by T1, which was 303. That's supposed to equal P2, which we don't know, multiplied by V2, which is 24, divided by T2, which is 313. Okay, so now that we've got all the information from the table into our equation, I need to scroll up and get a little more room here. Alrighty, so our job is to isolate that variable. We need to get x all by itself. What I want you to think of is this x as if it's being multiplied by the fraction, 24 over 313. You know that to undo multiplication, we would use division, and dividing is the same as multiplying by the reciprocal. So if I come over here and extend this fraction bar and multiply on the numerator by 313, you can see that those are going to cancel out. And also if we divide in the denominator by 24. So we've got the reciprocal of the 24 over 313. And of course what we do to one side, we have to do to the other. So let's extend that fraction bar, multiply by 313 in the numerator, and multiply by 24 in the denominator. All right, now I know you really want to start calculating things and clean up all these numbers here, but don't. Don't do it before you start multiplying by 313 or anything. Save all of this calculation for last. Matter of fact, that's so important that we're going to write it down. There are so many calculations in here, and none of these answers are going to come out to be nice, clean, whole numbers or integers. We're really not expecting that. We know that this is going to turn into some crazy decimal. So rather than have round-off error occurring in several different places in our calculations, we're going to save this calculation for last and set it all up so that we can do it at once. Okay, time to watch some common factors cancel. 24 over 24 is 1. 313 over 313 is 1. On the right-hand side, x is left all by itself. On the left-hand side, now we've got this mess. 313 multiplied by 22.7 multiplied by 17 divided by 24 and then divided again by 303. And now we are ready to work with your calculator. Let's see what we have. 313 multiplied by 22.7 multiplied by 17. If you're like me, I like to stop at this spot just so I can see everything and press enter because now I've cleaned up the numerator. And then when you divide, divide in two pieces. divide by 24, and then divide by 303. All right, and there we go. So our x, we're going to have to do a little rounding. X is about 16.6 psia, because remember, we get everything here in absolute terms. So the new pressure, we should probably turn it back into a gauge pressure because that's the way it was given to us. The new pressure takes this 16.6, subtract off the 14.7, and then we'll be here at 1.9. And this is psig. So that would be the gauge pressure that you would see for this situation. All right, not so bad, not so bad. Let's flip the page and try another one. Okay, here we go. Now we've actually got a situation. The low pressure side of an air conditioner compressor takes in 1.4 cubic inches of air at a temperature of -20 degrees Fahrenheit with a pressure of 12.7 psia. After being compressed, the new volume is 0.12 cubic inches with a pressure of 181 psia. All right, so first thing we want to do is fill in the table. Pause the recording, fill in everything you know on the given side, and then try to convert it over to the absolute side, and then come back when you're ready. All right, let's compare yours with mine and see how things are coming out here. The first thing that you want to notice is that the values for the pressure didn't change. They were already in absolute terms. We could leave those the way they were. And the volume numbers didn't change. Fahrenheit, not an absolute temperature, so we have to convert that one. And of course, to convert from Fahrenheit to Celsius, we just have to add 460, and that, of course, is where the 440 degrees Rankine comes from. And of course, the second temperature is unknown. So we're ready. Let's take the general law of perfect gas, P1 V1 over T1, P2, whoops, not R, but P, P2 V2 over T2, slide up and get a little more space, and fill in everything that we know. So let's see. P1 is 12.7. V1 is 1.4. T1 is 440. That's supposed to be equal to 181 times 0.12. Make sure you have your decimal point in the right spot. It's not 1.2. And then we have an x. So now we've got this interesting situation here where the x is in the denominator, and we need to get it out of there. So we have an interesting, we have a new step. We've done this before, but it was a long time ago. The way to get a variable out of the denominator is to multiply both sides of your equation by both denominators. So we're going to extend this fraction bar, multiply by x, and multiply by 440. And we'll do that on both sides. Multiply by x and multiply by 440. So you already know that, of course, you can do whatever you want to both sides of an equation. We should probably write down what we just did. Multiply both sides by both denominators. And let's see what that does for us. On the right-hand side, x over x cancels. And on the left-hand side, 440 over 440 cancels. So now the equation looks something like this. We've got x multiplied by 12.7 multiplied by 1.4 is equal to 181 multiplied by 0.12 multiplied by 440. Okay, I need some more space. You have bigger pieces of paper. All right, and so that cleared us, cleaned our equation up a little bit so that we don't have any more fractions to deal with, at least for a little while, but it got the x out of the denominator, which was the main goal. Now we're just going to use that division principle so that we get x all by itself. Right? X is being multiplied by stuff, so to undo the multiplication, we'll divide. Divide by the stuff exactly the way you see it. Remember, save those calculations for last. Watch all those common factors cancel. That's always the fun part. And so now x is equal to 181 multiplied by 0.12 multiplied by 440 divided by 12.7 and divided again by 1.4. All right, let's see what we have. 181 multiplied by 0.12 multiplied by 440. That should give me a value for the numerator. Divide by 12.7 and then take that answer and divide by 1.4. All right, there we are. Our value is, let's maybe round to the nearest tenth for a moment. X is equal to 537.5. Yeah. All right, 537.5 what? I'm going to have to go back up and check out my table. What was I doing anyway? Oh yes, there we go. T sub 2. That's a temperature. It's also a Rankine temperature. So these are degrees Rankine. Chances are the people that asked us this question would like to find out, oops, there we go, the temperature of the air in Fahrenheit because they gave us information in Fahrenheit. So when we get down to the bottom, let's make sure that we can convert things back for them and give them what they want to know in a nice, convenient, usable form. In order to go from Rankine to Fahrenheit, we just have to subtract 537, subtract the 460, and that turns out, whoops, sorry, 537.5. And that turns out to be 77.5 degrees. And those are degrees Fahrenheit. There. All right. That's really about as bad as it gets. There is no more difficult algebra than that. We just have to make sure that we're using absolute values for pressure and absolute values for temperature, and it works out pretty nicely. What's kind of neat is what happens if the temperature or the pressure or the volume stays constant. So we've got our general law of perfect gas here. If the volume stays constant and we don't know what it is, we just know that it's not changing, like maybe something's in a cylinder or a can, right, a spray can. The temperature may go up and the volume in the can isn't going to change at all. So if the volume stays constant, we would have P1 and the volume, I don't know what it is, but let's just call it C for constant, divided by T1, and P2, and there is that same C because the volume's not changing, divided by T2. And the cool thing about this is that, remember, I can do whatever I want to both sides of an equation. If I divide both sides of the equation by C, because of course the volume is not ever going to be 0, the C's become common factors and they cancel out. And so what we're left with is P1 over T1 is equal to P2 over T2. The volume doesn't matter if it doesn't change. We can do exactly the same thing if the pressure stays constant. We can have a constant pressure on both sides of the equation. Divide both sides of that equation by that constant pressure, and that becomes a common factor that just goes away. So we have V1 over T1 and V2 over T2, and those ratios should match. Exactly the same thing happens if the temperature stays constant. We would have, as a matter of fact, I'm just going to scroll up here a little more quickly. We would have P1 V1 over that constant temperature, and P2 V2 over that constant temperature. And this time we would just multiply both sides by that constant temperature, and that becomes a common factor. And so just like before, whoops, wrong color. If the quantity stays constant, it just doesn't matter in the equation. If you are reading a textbook, you might often see Charles's law and Boyle's law, and that's what we just figured out. We derived that from the general law of perfect gas. If the pressure of a gas stays constant, then the pressure just doesn't become a factor in the equation, and the rest of the equation stays the same. So we have V1 over T1 is equal to V2 over T2. So you can memorize Charles's laws if you want. If the volume stays constant, oops, P, I should erase that. If the volume stays constant, then we have the same equation that we had before without the volume value sitting there. And you can memorize these formulas if you like, or you can just use that general law of perfect gas and get that concept down that if one of these quantities stays constant, then you can just sort of cover it up and eliminate it from the equation. That's kind of neat and handy. At any rate, these have names. So Charles's laws are these two, and Boyle's law is what we would get here. I'll bring this back in a second. Boyle's law is what we would get when the temperature stays constant. There we go. P1 V1 is P2 times V2. All right, we'll erase that. Let's do that again. If the pressure stays constant, there you go, one of Charles's laws. So you see, that's kind of nice. The general law of perfect gas is all you need, and then that concept that if one of those quantities stays constant, we just eliminate its presence from the equation. All right, so let's try some like that. I'm going to let you take a second, read the situation, fill in everything where it belongs. Oh, actually, you know what? Maybe I won't. I'll help you out with this one here. At least get you started. Let's see. An oxygen cylinder gives a pressure of 2500 psig. When the temperature is 30 degrees Celsius. What should the gauge pressure be in the morning when the temperature is 20 degrees Celsius? So you see there's a lot of stuff in this table that we don't know. We're asked about the gauge pressure, so we're expecting to not know this one. The volume, well, it's in a cylinder. It's an oxygen cylinder. I don't know what the volume of the cylinder is, but I know that the cylinder itself is not going to change overnight. So whatever this is unknown, but constant. So we're just going to write constant all the way across. The volume is just not going to be a factor in our equation. All right, the second version of the second reading for the pressure is what we don't know. Your job is to decide what values, if any of these, need to be converted to put into the table. Now you can pause and come back when you're ready. How does yours compare? Hopefully it worked out pretty well. So if you wanted to go back to the page before, you could bring in and really write down that this is Charles's law. But really what is important here is that we know that the volume is not a factor, and we have P1 over T1 is supposed to equal P2 over T2. And then we just start calculating. Be real careful about where we put everything and that we're still using those absolute measurements. But here we go. 2,514.7 over 303 is equal to, there's our unknown, over 293. Okay, your job. Pause the recording again, figure out X, and then come back. Hopefully you just took what we had here, extended this fraction bar, and multiplied by 293 in the numerator on both sides, because that's what we need to do to isolate the variable. So X is worth 293 multiplied by 2,514.7, all divided by 303, and let's see what we get. 293 multiplied by 2,514.7 and divide by 303. There we go. Let's write that down. $2,431.7. Did we expect that? Well, let's see. The temperature went down, so yeah, that should cause a little relief in the pressure area. What are the units on this 2,431.7? Those should be PSIA, because that's the X in this absolute table. And of course, we were asked to find PSIG. So the gauge pressure is 2,431.7, but then we have to take out atmospheric pressure, oops, minus 14.7, subtract off, there we go, 14.7. And we are really looking for a gauge reading of 2,004, trouble here, trouble in River City. 2,417 PSIG. Okay, I better flip the page because this example is giving me some difficulty with my pen, isn't it? All right, let's got one more to do and then we'll call it good for today. So maybe you've heard about divers getting the bends if they come up too fast. That happens because the gas in their blood expands and expands so quickly that it forms bubbles. Let's see what we know about this particular dive. The lowest point, the pressure is 3,674 PSIA. And the volume of the gas in the blood is 3.05, and those are cubic inches. We rise to a different depth where the pressure is lower, 735 PSIA, and we want to find the new volume. Notice that the temperature we don't have, but the temperature should stay the same because this is in the person's blood. For the most part, we're assuming that they're not down there long enough for the body temperature to change much. So this is our constant. All right, your job, pause the recording, fill in the table over here with any changes that need to be made. Okay, what changes did you make? That's right, none, absolutely none. So let me get my table up there for you. There. Of course, we didn't need to make any changes because we already had the pressure given to us in absolute terms, and the temperature was constant, so we didn't need to worry about converting it. All right, if you flipped back a couple of pages, you would realize that we are in a situation where we are now using Boyle's law, because the temperature is staying constant, but essentially we're taking that general law of perfect gas and covering up the denominator of T because it's not a factor right now. So we have P1 times V1 is equal to P2 times V2. Fill in everything that we know. 3674 multiplied by 3.05 is equal to 735 multiplied by x. And you know how to solve this. You should finish this one off and then come back. Hopefully you've recognized that all that needs to happen is to divide both sides by 735. I need a little more space. There we go. So x is equal to 3674 multiplied by 3.05 divided by 735, and we'll do that on a calculator. 3674 times 3.05 divided by 735. And there we go. X is about approximately 15.25, round carefully, 15.25. Come back to our chart and see what we have here. Oh yes, that was a second volume. Those are cubic inches. Wow, that's quite an expansion, isn't it? From 3 cubic inches to more than 15 cubic inches of gas in your blood. I can see where that might hurt somebody's veins and arteries if that happened too quickly, huh? All right, and that's it. Get a good start on your homework, and we'll talk to you later. Take care. Have a great day.